Good morning, everybody. Okay, I've been grading your exams, and I'll be finished later this afternoon. I'll post the grades on Blackboard when I'm through, and I'll return the exams, and we'll go over the solution together in class on Thursday. Your next homework assignment, homework number 5, that's available right now on Blackboard, so you can get started on that after today's class. It's due on Tuesday, so you've got a week to solve that assignment.
You got the wrong date.
Okay, yeah.
I was kind of scared for a moment there.
Don't be scared. It's the 15th, Tuesday the 15th. Thank you for noticing that. All right. All right. Are there other questions? All right. Today we're going to talk about flow types and visualizations, and we may also have some time to get started talking about flow acceleration. And this is an exciting part of the course because this is where we kind of turn the corner from just talking about static conditions where the fluid is never moving into the more common and the more important situation of fluids that are moving from place to place. So it's the point where we're going to learn a lot more equations that handle a lot broader cross-section of conditions. So, like I just mentioned, thus far in the course, we've just been dealing with statics. So talking about fluids that are stationary and not moving. But understanding the behavior of fluids when they're moving is important because most of the water in the world is moving from place to place. Whether it's through a pipe, through an open channel, it's the moving fluids that engineers are often called on to analyze and design for. And so that's why fluid motion matters. And the types of things that we're going to try and learn how to predict, like the equations that we're going to be developing and using, are equations that will predict what is the pressure as fluid is moving from place to place, or how much energy is lost when fluid moves from place to place, or when you have a known pressure decrease, what's the distance over which it occurs. So that's just a few of the types of problems that we'll be able to solve once we have a handle on how to describe the motion of fluid. Now broadly speaking, there's two main approaches to handling fluids that flow. And the Lagrangian approach answers the question of what is the fluid velocity by trying to track individual particles through space and time. And the idea is that if you know a particle and you track the path that it takes, then you can use the equations that we've got to predict how the change in pressure is going to occur over the path that the individual particle is taking. So the path of the particle will exist in 3 dimensions and will have to, either in a problem you'll be given just a 1-dimensional flow, or in some cases 2. We won't deal with 3-dimensional flow in this course, but you'll have the location of the particle over time, and you'll determine the velocity of the particle by looking at its change in position over a period of time. Now, the Lagrangian approach is not used a lot simply because in a given system there are a lot of particles, too many particles to keep track of individually. And so what we have to do instead is we have to have representations of particles so that we can kind of aggregate them together, and instead of tracking each one of them and the path of each individual particles, what we'll do more often is apply the Eulerian approach, which answers the question, what is the velocity, by looking at a certain location in space and continuing to observe that location over a period of time, and using the flow conditions at one point to represent everything that's happening inside of an element. And so essentially what we're doing is we're creating a mesh in the flow field, or a window, and each one of these pixels inside of the mesh is going to have a flow velocity assigned to it, and that flow velocity is assumed to apply to everything inside of that element. So you'll have to track particles, but far fewer particles, and then you're just assigning everything the same characteristics as the one particle that you are tracking. It's representative. So we'll still have some situations where we're looking at the position of particles, and that can be expressed in 3 dimensions, and the velocity in each of the 3 coordinates will be analyzed over an increment of time to know the acceleration that occurs, and it's the acceleration that drives a change in pressure. So there's a lot of information that we can get from photos and even more from videos of flowing fluids. And so there's a stationary object here, a model, and I bet everyone here would guess that this is a picture that's taken in a wind tunnel. And so what sorts of information can we get from the picture? Yeah.
Well, depending on what direction the blowing force is that it's splitting up. One's going over the car and another one's going underneath it.
Okay, good. And you brought up an interesting question. What direction is the fluid flowing? In this case, the fluid is a gas. It's air. And can we tell from the photo whether, like, which direction the air is blowing? Is it blowing from the passenger side towards the driver's side? No, I see some heads shaking.
Front to back.
You're right. It's front to back. And what was the clue that tells us the flow is going from front to back?
The stream of air looks more solid from the front. And
Okay.
It sort of disperses by the back.
Very good. So he's noticing that we've got this tracer that's being injected into the wind tunnel. And this tracer is maybe just like some smoke. And the tracer is less diffuse in the front than it is in the back. And we all kind of have a notion that, like, for instance, if you threw a smoke bomb in the corner of the room, it would begin to diffuse outward over time. And the same diffusion is occurring here, where in addition to the air packets blowing from front to back, the air is also mixing sideways. And so the smoke here is kind of together, because it's not shown on the screen here, but there's probably a pipe of some sort with a nozzle at different elevations, and it's injecting the smoke into the wind tunnel. But then by the time you get here, it's becoming more faint and mixing with the surrounding air. So that tells us the direction. Now, the other interesting factor that this tracer can show us is where the wind is being deflected. And so we can see that the windscreen is deflecting the flow of the fluid up, and you'll notice that there is a decrease in the distance between this tracer gas. Now, it's kind of hard to see exactly because we're looking at it from an angle, and so part of the reason why this appears to be closer together here compared to here is that this part is further away from us. And so our mind has to kind of simultaneously correct for the perspective effect, but then also the fact that these streamlines, as they're called, are getting closer together. And what that indicates is that there's a relative increase in the velocity when these streamlines are getting closer together. That's kind of the reason why on the back of a lot of cars, what's this called on the back? Spoiler. Spoiler alert, it's called a spoiler. So the purpose of the spoiler is to spoil the lift that generally occurs as the wind goes over a car, because the Bernoulli principle, which you probably have heard in other contexts before, is that a gas that travels over the top of a wing is going to have a higher velocity than the gas that goes under a wing, and that higher velocity corresponds to a lower pressure. And so what we have on top of the wing shape is high velocity and therefore low pressure, whereas on the bottom of the wing is low velocity and therefore higher pressure. We'll talk a lot more about that later next week when we talk about the Bernoulli equation in detail. But that's the general principle, and that's why airplanes can fly, is that on the top part of a wing the pressure is low, and the difference in pressure creates lift. So the difference in pressure enacted over an area, pressure times area gives you a force. And so that's how there's equilibrium between the weight of the plane acting downward and the lift force, which is acting upward. So here in this picture, to get this car back to a wing, you may be saying, well, this is a car, not a wing. But look at the cross-sectional shape of this vehicle. It's flat under the vehicle, and the rounded shape along the top kind of in some ways resembles a wing. So unintentionally, vehicles can produce lift, and at high speeds, that's not great for traction. When the car is tending to kind of like its weight is reduced and it wants to fly in effect, and so the purpose of the spoiler is to put a little bit of extra force on the back wheels to try and spoil the lift effect that otherwise would occur. So as it relates to flow visualization, which is what we're talking about right now, these streamlines getting closer together, they don't tell us exactly what the wind speed is. We can't tell from this photo whether the wind going over this vehicle is 10 miles per hour or 100 miles per hour. But what we can tell is that on a relative basis, the wind is faster where these two lines get closer together. When two streamlines get closer together, that's an indication that acceleration has occurred. So we're going to talk about that in detail today. Any questions about this picture and some of the information we can glean from that? All right. So I've already used this word a couple of times today, streamlines. And a streamline is a way to represent the local velocity. And here we have streamlines in an open channel. So you can see that the water is flowing downhill. These little black marks at the top are meant to illustrate like the ripples of water, so it means that it's open to the atmosphere. Whereas in this case, it's a cross-sectional view of flow through a pipe. Now in both cases, you can get an idea that the water is flowing from the left to the right because these streamlines have arrow tips on them. And so you get an idea of the direction, but we can't tell the magnitude of the velocity through the river or through the pipe. We just can see the direction. And in this case, as water is flowing down through a tank and discharging through an orifice, we get a little bit more information. Because we can see that when these streamlines are getting closer together, that indicates an acceleration. So think about as the water approaches this opening, it's accelerating. There's a high velocity as the water discharges out of the orifice because essentially you've got an opening in the tank that's below the water surface, and so there's some pressure down here, and that pressure is forcing the fluid through the opening. Later in the semester we'll actually do an experiment in the lab where we have an orifice connected to a tank, and we're going to look at the velocity of the water as it exits out of the tank and try and relate that to the height of the water above the orifice. But for today, we just want to point out that the streamlines at every point will indicate the velocity of the fluid, its direction. And so you'll notice here at A, they've drawn an arrow that's tangent to the streamline, because when the fluid particle is at this location, its velocity is tangent to that streamline. But then its velocity is changing as it approaches the orifice. Now there's two components to velocity. There's magnitude and direction. And here in this diagram, we're getting an idea that the direction and the magnitude of velocity is changing. The direction we can see just because the streamline is curved, and then the magnitude, we can tell the magnitude of the velocity is changing because these streamlines are getting closer together, which just means that the velocity is increasing as we get closer and closer to the orifice. This is showing some streamlines going over a wing shape. And so you notice that there's a certain point where a streamline is intersecting the leading edge of that airfoil, and it's identified as a stagnation point. And simply what that means is that there's some velocity in the air that's moving over, that's approaching the wing, and suddenly just a certain amount of that air stops on the leading edge and doesn't go over and doesn't go under. There's just a point of stagnation, and that causes a local accumulation in the pressure on the leading edge of the wing. Later on we'll talk about how you can calculate how much extra pressure there is at the stagnation point. But for now we just want to think of streamlines as a tool that we have for understanding velocity. It will help us to understand the direction and the relative magnitude. So in this depiction we have a nozzle where the diameter of a pipe is decreasing. And if the diameter of the pipe is decreasing, but we have the same flow rate going in and out, so we're saying that, if we have a flow rate of 1 liter per second going into that nozzle, 1 liter per second is going in, 1 liter per second is going out. Since the diameter is decreasing in the nozzle, then that means that the velocity has to be increasing. And that's what the streamlines, that's the story that they tell, is that the velocity is increasing because the lines are getting closer together. Now, we're going to divide flow into different categories because there's different equations we use to describe the performance and the behavior of water depending on what kind of flow it's experiencing. So if we have open channel flow, we use one set of equations. If we have pipe flow, we'll use a different set of equations. In this case, what I'm going to illustrate is the difference between uniform flow and non-uniform. So uniform flow is when the velocity is constant along the streamline. So that means in the direction of flow, velocity is constant and not changing. So if the velocity isn't changing, then the streamlines will be straight and parallel. Remember, they get closer together or further apart when the velocity is increasing or decreasing on a relative basis. But here, they're straight, parallel, so this is uniform flow. The change in velocity with respect to position is 0. Uniform. Now, non-uniform is just meaning that the velocity does change with respect to position. And so the streamlines won't be parallel any longer. They'll be curved. So that case of the fluid that's entering a nozzle that's contracting the diameter, that's a case of non-uniform flow. We can see that these streamlines are approaching each other. They're converging as the fluid is accelerating. And so if the velocity is changing, it's not uniform. Now here is some rotational flow. And even if the magnitude of the velocity is the same as the water swirls around in a circle, the direction is changing. And remember that velocity has two components. It's got magnitude and direction. And if either one of them is changing, then that means it's non-uniform flow. So back to the earlier slide, this is non-uniform flow because the velocity is changing with respect to position as the fluid approaches the orifice. Next semester, for those of you who will continue on to hydraulic engineering, a lot of the equations we use for design of open channels assume uniform flow. It just makes our calculation so much easier if we have water flowing through like a channel that's straight and uniform. Maybe when we see those in the real world, they're often like concrete lined channels. But in the real world, when you consider like flow through a river or a stream, most of the time what you're experiencing is non-uniform flow, where water is going around a bend, or when the river is getting narrower, or maybe a channel is getting deeper or more shallow. So to handle that, what we often have to do is break a river into segments and say, well, this segment, the flow is relatively uniform here, but then it changes direction. And so we take that kind of approach of breaking a flow situation up into elements and considering them individually. So just a preview of things to come. So one way that we can classify flow is whether it's uniform or non-uniform. Another thing that we can do is we can look at how conditions maybe are changing over time. Uniform is all about position. Steady versus unsteady is how flow may be constant or changing, with respect to time. So steady flow says that there's no change in the flow velocity over time. So that change is 0. Unsteady flow means that the velocity at a single point in the streamline is changing over time. Now, we had pictures to show the difference between uniform and non-uniform, but we can't use just an individual image to illustrate the difference between steady and unsteady flow, because of course a photo is an image just at one instant in time. So to look at how it's changing over a period, we would have to use a series of images. So that's to say like a video or a time lapse or something. So here's an illustration of some pretty exciting unsteady flow. Let me pause my recording or my video will get that. They're hiking along. It's just a dry creek bed, and upstream in this watershed there was a quick rain burst. You know, it started raining very intensely some distance away. If you listen to his dialogue, he said that they didn't even know it was raining, because it doesn't have to rain where you're at, it just has to rain somewhere else in the watershed. And this area has lots of rocks in it that aren't going to absorb or retain water. And so the water that falls on the ground, since it's very steep canyon conditions and water isn't infiltrating into the soil, just the water is able to concentrate and get into the channels really quickly. So this flash flood just illustrates that the flow conditions were changing over time, and by the end the water's moving fast enough that it could very easily sweep somebody off their feet and bang them into a rock and fill their mouth with water. So it's very dangerous conditions, but that's just an illustration of what we mean by unsteady flow. Flow conditions were changing over time, and it's very easy to observe. There are other ways that we can categorize and classify flow besides steady, unsteady, uniform, non-uniform. So a third method of classifying flow is whether the flow is laminar or turbulent. Laminar flow is characteristic of slow-moving fluids or fluids that are highly viscous. And there's a parameter called the Reynolds number. Here's the formula for the Reynolds number. You can see it's the density, the velocity of the fluid, the diameter of the channel, so diameter of an enclosed pipe, and then the viscosity of the fluid. And this viscosity is the absolute viscosity. That's one way of expressing the Reynolds number. Another is, if you remember kinematic viscosity, remember that kinematic viscosity is absolute viscosity divided by density. And so with that definition of kinematic viscosity, another way we can calculate the Reynolds number is the velocity times the diameter of the channel divided by the kinematic viscosity. And this is usually the one I'll use just because it's one fewer variable. The kinematic viscosity takes into account both the viscosity and the density. But now consider, if we're saying the Reynolds number, the limit for Reynolds number is 2,000 for conditions to be laminar. If you go above 2,000, then the conditions are no longer laminar. So here in this formula, if you want the Reynolds number to be less than 2,000, then that means the velocity can't be too large, the diameter can't be too large. That would increase the Reynolds number. And what helps you to have a low Reynolds number would be a big denominator. And so a fluid with a high viscosity. So fluids that you think of as being really thick, they flow with laminar conditions really easily. If you're pouring the honey out of a container and it's flowing really slowly, it could be that you have laminar conditions there. Laminar usually means that there's not a lot of turbulence in the channel as the water is flowing. You'll notice that this velocity profile is relatively smooth. Essentially means that the water's moving slow enough that if a fluid particle bounces into the side of the channel, it kind of just comes back to where it was before. It doesn't start a whole chain reaction of there being so much extra energy in the fluid that then there's lots of rapid mixing with the other particles. It means that the flow conditions are relatively quiescent, meaning very calm. In contrast, turbulent conditions occur when the Reynolds number is greater than 4,000. And so turbulent conditions, you still use the same Reynolds number to calculate RE. It's just that you usually will have turbulent conditions if the velocity is high. It's more common in fluids with a lower viscosity like alcohol, water. Those fluids have relatively low viscosity. So it's common in pipes. In a ship's wake, you'd see turbulent flow conditions. And there's more energy loss when fluid is flowing in turbulent conditions than when flow conditions are laminar. You'll notice that there's some space in between what's laminar and turbulent, and we just call that transition flow when it's between the two. During the experiment we'll do in the lab to visualize laminar versus turbulent flow, what we're going to do is we're going to try and, with our eyes, see if we can identify the point at which the fluid becomes turbulent and starts to mix. So we'll see if these Reynolds numbers that are typically held, 4,000, that's a rule of thumb. But anytime you see a nice round number like this, you should be skeptical. Like, who decided it was 4,000? Like, maybe if it was 4,187, it's like some odd number, then you say, oh, maybe that's actually been measured. But 4,000 is awfully arbitrary. So we'll see from our experimental standpoint what we think the dividing line between laminar and turbulent flow conditions is.
So what would you get if you were between 2,000 and 4,000? Like what state would that be?
It's called transition flow, and the way it works is, let's say you have a pipe, and the flow is moving very slowly through the pipe. So the slow-moving flow conditions would be laminar, but we're opening a valve downstream. So as we open the valve, the velocity is increasing. So the Reynolds number is slowly going up and up. So let's say that now we've crossed the threshold of 2,000, but we came at it from the direction of the laminar side of the dividing line. The flow conditions would stay laminar until there was some sort of a disruption, like if you hit the pipe with a hammer and induced some turbulence, or once you get beyond 4,000. Then the turbulent flow will occur. And so what we'd say is we have a graph of Reynolds number. So here is 0 Reynolds number, and here's 2,000, here's 4,000. So we're saying that this is the laminar region, this is the turbulent region, and here is transition. Flow conditions will stay laminar if you have been previously laminar. If you're coming from the turbulent side, like if you had a really fast-moving water velocity and it was already turbulent, but you're closing the valve now, so you're decreasing the velocity, it would stay turbulent until you got to the 2,000 threshold, approximately. So in contrast to a nice bullet-shaped parabolic velocity profile, when we have turbulent flow conditions, there's a lot of variation. And so here you'll see that jagged line is just telling us that there may be a certain point in the flow field where the velocity at that particular spot is less than the average velocity. There may be some locations where the local velocity is higher than the average velocity. And you'll also notice that this is flattened out, the parabolic shape. And so we no longer have this distribution in the velocity profile. So just to get some practice calculating the Reynolds number, I'd like you to first, in step A, calculate the Reynolds number for water that's flowing through a 2.5 meter diameter pipe, and the velocity is 0.1 meter per second. Anybody have the viscosity of water memorized? You will by the end of the semester. All right. So the absolute viscosity is 1 times 10 to the minus 3 newton seconds per meter squared. Or if we want to do it in kinematic terms, it's 1 times 10 to the minus 6 meters squared per second. And that's at typical 20 degrees Celsius conditions. If it was at a different temperature, then your viscosity would be slightly different. But that's for water. All right, so that's step A, and then in B, consider how high can you take the flow velocity for these conditions? What's the maximum velocity that will give you laminar flow conditions?
No, this is water around fluid, correct?
Yep, we're talking about water. Yep.
All right.
I was like, he's going to go home and tell his wife that the student called him a hoe.
All right, so even when the water is going just 0.1 meter per second, so we're talking, that's just inches per second through this pipe, then what we'll see is that the flow conditions are turbulent. Anybody else get a Reynolds number of 250,000? Yeah, so that's really high. It kind of illustrates how rare laminar flow conditions actually are. By the way, if you look at the units of Reynolds number, it turns out to be unitless. So we had velocity times diameter divided by kinematic viscosity. So in the numerator, that was meter squared per second. In the denominator, meter squared per second. So it cancels out to be unitless. So through the pipe, the conditions are turbulent. Now, there's a certain section of the pipe where flow conditions are laminar. If I go back to this sketch, remember that the velocity isn't the same everywhere. The velocity in the center of the pipe is faster than the velocity at the edge of the pipe. Anybody have a guess on why that is? Like, why is the velocity in the center of the pipe faster than the velocity at the edge?
Difference in pressure?
It's not difference in pressure.
In the pipe pulling the water back.
It's the resistance. Yeah, so you remember when we were talking about viscosity, we talked about if the water is flowing from left to right, the pipe wall is resisting that fluid movement. So the pipe wall is pushing to the left, and so the velocity is the lowest at the edge. So even though when we said in this example the velocity is 0.1 meters per second, that was talking about the average velocity. But here, when you get really close to the edge of the pipe, remember we assume that the flow velocity is actually zero. The fluid, that fluid particle that's like the one molecule that's just above the edge of the pipe, it's moving at a velocity of zero. It's stationary. And so there is a section that's laminar, kind of like you can think of it as a cushion that goes around the outside edge of the pipe, where the flow conditions are low enough inside of that cushion that you have laminar flow inside that ring, that outer ring of fluid that's on the edge of the pipe. And so how thick is the laminar region is dependent on the velocity. So if you have a really slow-moving fluid flow, then that laminar region will be very thick. Yeah.
So on the Reynolds number, the number is always, the main difference in number is the velocity. The density, the viscosity, and the diameter is a constant for most of the equation, right?
No, the diameter can be a variable. You know, we have a lot of different pipe diameters available when we're sizing a pipe network. So you do need to pay attention to the diameter, but I mean, the fluid characteristics don't change a lot in civil engineering. You know, for us civil engineers, usually water is what we're dealing with. Temperature is going to change it a little bit. The mechanical engineers have things a little bit harder because more often they're going to be concerned with air and hydraulic fluids and oils and water. So, all right, so what about this part B? What's the maximum flow velocity that we can have and still experience fully laminar flow, meaning through the entire thickness of the pipe? Well, the maximum velocity that you could have is 0.8 millimeters per second. Now, if it's faster than that, that just means that in the center part of the pipe, where the fluid's moving the fastest, then it won't be laminar in that center pipe, the center part of the pipe. So we'll talk more about like the thickness of the laminar sublayer at a later date. Any questions about this example? All right, so this is important. We're going to fill out a slide like this with lots of compare and contrast information over the course of the next several lectures. Right now, the slide's relatively empty because we haven't gotten into all the details and all the implications. But when we talk about flowing fluids, remember that one of the ways that we could characterize and classify the fluid is if the flow is uniform versus non-uniform. And then also we talked about steady versus unsteady. So whether it's uniform or non-uniform, the change in velocity with respect to position is under consideration. Steady versus unsteady is change in velocity with respect to time. So in future classes, I'm going to be making this list longer and telling you like which equation goes in which of these columns and what's being affected by a change in velocity with respect to position, and like what type of acceleration will cause each. Anytime there's a change in velocity, there's an acceleration that caused it. But there's different kinds of acceleration. All right, so streamlines you've already heard about. Path lines are what happens when you track the movement of a particle over time. So for instance, if you threw a bottle into the Ohio River and then you had an aerial view of that bottle and where it went over time, you could do kind of like a dot that every 1 second would trace the movement of that particle over time. A streak line is a little bit different way to observe the history of flow. Instead of just tracking a single particle, what happens in a streak line is there's the injection of a tracer at a fixed point, and then the streak will tell you the history of the flow. So if you're standing out on a pier and you're pouring paint into the ocean, then you could kind of watch where that paint goes, and it would tell you how the flow was moving in the ocean. So if I was pouring paint into the ocean and I looked off to my right and I saw all the paint was being spread in that direction, then where my tracer was being moved would tell me more about like the flow as a whole. All right, so for the next illustration, consider that we have a couple of different time periods. So the scenario is that there's a dividing line in time. There's T naught is kind of like before T naught, the water's flowing to the right, and then after this certain period in time, the water's starting to flow in a different direction, up and to the right. So keep that in mind. There's a before and an after, and the fluid is moving in two different directions, before and after. So in this diagram, which is from your textbook, it's showing, first of all, the streamlines. We've got the streamlines before, which are flowing to the right, and then the streamlines after, which are up and to the right. And what this is showing is the difference between a path line and a streak line. So the path line is shown with these black dots. So if we dropped a particle into the flow, then the flow would move the particle to the right until T naught, and then at T naught that particle would change direction and it would start to flow up and to the right. And so that's what we see here, is that after T naught the fluid started moving the particle in a different direction. And so what we're looking at is the history of that particle's location, and it tells a story of what was the velocity, both the magnitude and the direction. If we know that these dots were drawn every 1 second, then we can find the magnitude of the velocity just by the length of the line and the time period that elapsed between each one of these dots. Here's the streak line. And we always were injecting the tracer at the same location. And so over here, this is the first bit of tracer that got injected to the fluid. If this is paint that we're pouring in, the first bit of paint was this because it got pushed to the right during the period before T naught. And then after T naught, everything got shifted up and to the right. And so here's that same starting point. Those first few molecules of paint are here, and they've got everything shifted upwards and to the right. And so this horizontal segment of the streak line got pushed upward during the second period of time. So it kind of looks like they're just the inverse of each other. That's not necessarily always the case. That's just coincidental in this illustration, that the streak line and the path line appear to somehow be like a mirror image. To get some practice with streak lines and path lines, I'm going to give you this handout, and we're going to consider water flowing during 3 periods. No, wait. The handout's a different one. All right. I'm going to do this illustration on the board, and you can follow along just on a scratch piece of paper if you've got one, and then we'll do the handout. What we're looking at here is that here's the particle starting point. We want to follow this object as it moves around during these 3 time periods. And so 9 seconds where it's being pushed to the right, 4 seconds it's being pushed down, and then 6 seconds it's being pushed to the left. And so the path line would look like this. I'm going to put a dot every second of movement. It starts here, and it's going 1, 2, 3, 4, 5, 6, 7, 8, 9. And then down for 4, 1, 2, 3, 4, and then over 6. 1, 2, 3, 4, 5, 6. And then here's the end. And so then I connect the dots, and this is my path line. Path lines are easy to draw. Streak lines are a little bit less obvious. And so the suggestion that I usually make to draw a streak line is, instead of moving your pencil or pen, move the paper in the direction that's indicated by the arrows. So what I mean by move the paper is, we're saying that the paper represents the flow field, and we're injecting some tracer at the same location. And so if you move your paper to the right for 9 seconds while you hold your pen steady, and then you move the paper down for 4 seconds, and then you move the paper to the left for 6, and each time you're moving it, you're moving the paper at the same velocity, then the shape that you're going to end up with is like this, where we've got the starting point and the ending point, and then your pen would still be on the page when you came to a rest after that final 6 seconds. So just keep in mind that my suggestion on how to draw the streak line is to move the paper. Now the tricky thing, though, is that you don't know where the pen is going to end until you stopped. And so I usually, if I want to draw it to scale, I will get the shape of the streak line, like just freehanding it, or maybe on some scratch paper, and then I will redraw the streak line with this point, the ending point, being at the location I know the tracer is being injected. So on the handout I'm giving you, there's a spot to do the path line, and then I've given you 2 windows for the streak line. And the reason why is that this grid on the right, I intend for you to get the shape of the streak line, and then you transfer that shape onto the grid on the left. And B, which is on here, is where the tracer is being injected the whole time. And so B is where your streak line should end. All right, so let me hand this out to you so you can look it over. Okay, so the path line is relatively straightforward to sketch out. You're just moving this particle in the direction that's specified by the arrows. The streak line, though, what I generally do will draw the shape off to the side, and then the reason why I'm doing that is I don't know exactly where the ending point is going to be. So then once I get the shape of it, I can move that so that it makes it at the ending point at the location I want it to be. And I suppose if I went backwards through time, I probably could do that. But streak line and path line are two different approaches that you can use to understand the history of the flow and the magnitude of the velocity and how the direction has changed. All right. Let's talk about flow acceleration. We've been talking about changes in velocity, and so it's acceleration that's associated with the change in velocity. And if we have particle moving along a path line, there's two components of its acceleration. The component that's tangential and that's normal. And the total acceleration is going to be the change of the particle's acceleration over time, the change in velocity with respect to time, and the change in velocity with respect to position. And the change in velocity over time we call local acceleration, and the change in velocity with respect to position we call convective acceleration. Let's look at an illustration of both. We'll start with the change in velocity with respect to position. Man, yeah, I'd rather work in an office than sit in a tube like that and get knocked unconscious by G-forces. But so what it was saying is that, remember, velocity has two components, and even though the speed is constant, you know, the speed, the magnitude of the velocity isn't changing. The fact that the person inside of that tube is changing direction means that there's a centripetal force there. And so that's one kind of acceleration. The other illustration of acceleration we'll take a quick look at is with a rocket sled. So I don't know if you noticed that, but at one point the ejection seat, where did it fire? It's so quick we didn't even see it. Well, we all saw it, right? Oh, there it is. There it goes. So it was stationary to begin with. They lit the rocket, and by the end it was going several hundred miles per hour, and that is local acceleration. So a particle that's moving through time and through a space will have to integrate and consider all of the acceleration in all three directions, and both the change in velocity with respect to position and also the change in velocity with respect to time. So we'll consider those individually. The local acceleration occurs when the flow conditions are unsteady. So remember, steady, what we were talking about before was the picture of that flash flood in the canyon, where there was a difference between the velocity of the water before and after. The before, there was no velocity because there was no fluid moving through that channel, but then the after, it had a pretty high velocity. So conditions were changing over time, and that's local acceleration, the change in velocity and the change in time. In contrast to that, convective acceleration occurs when the conditions are non-uniform. Time has nothing to do with it. The magnitude of the velocity isn't changing over time. What's changing is the magnitude of the velocity with respect to position. Now here I've got a nozzle depicted in this image, and what it is a pipe with a converging diameter, and at one point in the opening of the nozzle, the diameter of the pipe is such that it's causing a velocity of 10 meters per second. And then on the discharge end, the velocity is 20 meters per second. because the diameter of the pipe decreased. And so anytime there's a change in velocity, we know that there had to have been an acceleration. But the acceleration is occurring even though the flow conditions are steady over time. So steady means no change over time. And so right now and an hour from now, maybe I'll have the same inflow and outflow from that nozzle, over the course of an hour. So conditions can be steady, but there's still an acceleration because the velocity is higher in the discharge end than the inlet. So that's convective acceleration. So we're going to fill in this table a little bit more when we're comparing and contrasting uniform versus non-uniform, steady versus unsteady. So they're both about changing velocities. One is the changing velocity over time. One is changing velocity over position. So the acceleration that's associated with non-uniform flow is convective, and the acceleration that's associated with unsteady flow is local acceleration. Here is the equation for convective acceleration. Convective acceleration is described at a single location. And so the convective acceleration at a single spot is the velocity at that location, and then the change in velocity with respect to position. And so this du dx is a representation of how the velocity is changing as you move through space. And so this nozzle that I showed you before, let's say that, for example, we have some formula that allows us to describe what's the velocity as we move further away from this axis, so in the x direction. So what this formula is saying is that when we start here at x equals 0, the velocity is just going to be u naught, so 10 meters per second. But then by the time we get all the way to L, so when x equals L, then that would be u naught, meaning 10, divided by 1 minus 0.5. So it would be divided by 0.5, which is going to double the velocity. But here in the middle is maybe where we're interested to know what's the convective acceleration. We want to know how much acceleration is occurring at a single point in space. And so what we have to do is we have to find du dx and calculate the convective acceleration based on that. Well, you may be in luck. If I don't have my notes, then we'll have to pick this part up on Thursday. I found my notes. Where did I? Well, yeah, I'm not going to keep you any longer. I thought I had it out earlier. Maybe I took it out in my office to review. What we're going to do when we get together on Thursday, we're going to take a look at finding the derivative of this velocity function and multiplying it by the velocity at a certain location. So at the midpoint, if we know that L is If we know that L is 0.5, what we'll do on Thursday is we'll look at here in the middle, substituting that known location into the velocity function. We'll find out what's the velocity there, and then we'll find out what is the rate of change in velocity with respect to position. So that's where things are headed. Remember that the next homework assignment is already posted on Blackboard, so you can get started with the, there's a couple problems like this flow visualization stuff. There are a couple of problems where I'm asking you to think about like your study strategies this semester, just kind of like some general questions. Now that we're partway through the semester and you know what this is going to be like, you know what the homework is like, my instructional style, I'd like to hear your feedback on if you have any suggestions for improving the course and your own ideas about how you plan to study and be successful through the semester. So have a look at that assignment. It's due a week from today, and I'll see you on Thursday.